Hi everyone, today I can find approximate trig ratios using the TI graphing calculator. I can solve trig equations and find angle values using the graphing calculator, and I can use Pythagorean identities and double angle formulas. In example 1, we're finding approximate trig ratios on the calculator. It's really important to know what mode to set your calculator in. If we're given an angle in degrees, we want to have our calculator in degree mode, and if we are given an angle in radian form, we want to set our calculator in radian mode. When we're approaching these problems, we need to pay really close attention to the mode. Okay, so in this first example, because I see a degree symbol, we need to make sure our calculator mode is in degrees. If I go over to my calculator, the first thing I'm going to do is go to the mode button and make sure that my mode is in degrees. So I'm going to press enter, and then I'll quit out of that. All right, and the first problem says sine of 78 degrees. So I am just pressing on the sine button, sine of 78 degrees. I'm pressing enter, and we get 0.9781 approximately. So 0.9781. Going on to the second example, we need to make sure that our mode here is in radians. And I know that I'm using the radian mode because there's no degree symbol. Okay, so going over to my calculator, I'm changing my mode, and I'm going to set my mode in radians. Quit out of that, and I'm just using the cosine button. Cosine of 4 pi over 3. So I'm doing 4 second. We get pi that way over, over 5 is what it is. Okay. So we get negative 0.8090 there. Okay, so negative 0.8090. Over here on example 3, we're using secant of 3.91. Again, the mode should be in radian form just because there's no degree symbol. Now, we don't have a secant button on our calculator. I see sine, cosine, and tangent. So I need to know that secant is just the reciprocal of cosine here to help me. So in my calculator, I'm going to type in 1 divided by the cosine of 3.91. Okay. So going back over here, 1 divided by the cosine of 3.91. Again, just double check your calculator in this case should be in radian mode, which ours is. So I'm just going to press enter, and we get negative 1.390, and I'm going to round that up to 8. Negative 1.3908. Okay. Let's go on to the next section. In this section, we're going to need to know the range of inverse trig functions. Okay, so for arcsine, or it looks like this, sine inverse, arctan or tan inverse, or arc cosecant or cosecant inverse, we are using quadrants 1 and 4. We're going from negative pi over 2 to pi over 2. So we are only going to see answers in quadrants 1 and 4. For arc cosine or cosine inverse, arc cotangent or cotangent inverse, and arc secant or secant inverse, we are going to be going from 0 to pi. So our answers will just be in quadrants 1 and 2. Okay, so we've got to keep that in mind. All right, so looking at this first example here, it says find the angle values in degrees for theta to the nearest degree. Okay, and we're going between 0 and 360. It can be equal to 0, but it has to be strictly less than 360 degrees. Let's just keep that in mind. Okay, so we've got sine theta equals 2/3. We have to try to get theta by itself. We're trying to solve for theta. So what I'm going to do is I'm going to use inverse sine to undo the sine function. Whatever I do to one side, I have to do to the other side as well. So I'm writing sine inverse of 2/3. Okay, so really this is what it looks like all written out. Sine inverse of sine theta equals sine inverse of 2/3. You can see that sine inverse undoes the sine function and just leaves me with theta. And on the right-hand side, I'm left with sine inverse of 2 over 3. Okay, so we need to think about what mode we want to be in. Well, because we want our answers to the nearest degree, we need to make sure that we are in degree mode on our calculator. Okay, so in my calculator, I'm going to use sine inverse, which is just right above the sine button. So I'm going to do second sine in order to get sine inverse to pop up. And I'm going to type in 2 over 3. Okay, again, we want to make sure our mode's in degrees. Right now, I think our mode is in radians. So let's just go ahead and change that to degrees. Enter. I'm going to click out of that. Okay, and then I'm going to press enter here. So there we go. We get degrees. About 41.81 degrees. So theta equals 41.81 degrees. Now, we're not quite done yet. Now remember, when we put this into our calculator and we get 41.81 degrees, all my calculator is capable of when I'm entering in sine inverse is finding answers in quadrants 1 and 4 for sine inverse. But we know that there is more than one spot where sine is going to be a positive value. All students take calculus. We know that sine is not only positive in this first quadrant here, but sine is also going to be positive in the second quadrant as well. So I'm going to think to myself, okay, in the first quadrant, I just got a reference angle of 41.81. If we use that same reference angle in the second quadrant, what would be the measurement of this angle? Well, in order to get the measurement of that angle, I'm going to take 180 degrees and subtract off the 41.81 chunk. And I'm going to be left with 138.19 degrees. Okay, so not only is my answer going to include 41.81, but it's also going to include 138.19 degrees. Okay, moving on to number 2. We've got cosine of theta equals negative 0.5. To undo cosine, we're going to use cosine inverse on both sides. So my left side is theta, and my right side would be cosine inverse of negative 0.5. Okay, I'm going to go ahead and type that into my calculator. Second cosine of negative 0.5. Again, our mode's in degrees because we wanted our answer to be in degrees, and we get 120 degrees there. Now remember, my calculator is only capable for cosine of giving me answers in quadrants 1 and 2. My calculator is not considering quadrants 3 and 4. So I have to think to myself, is there anywhere else where cosine would be negative? So I'm going to draw my picture. All students take calculus. Cosine would be negative in not only quadrant 2, but also quadrant 3. So in quadrant 2, we got that this was 120 degrees. So my reference angle would end up being what? Well, in order to get my reference angle, I'm going to do 180 minus 120. So we get a reference angle of 60 degrees. If I use that same reference angle in the third quadrant here, what would I get for my original angle? What is 60 degrees more than 180? Well, 180 plus 60 is going to give me 240 degrees. Okay, again, I did 180 plus 60, and we end up getting 240 degrees. So I'm going to include that as part of my answer. Not only am I going to put 120 degrees, but I'm also going to put 240 degrees, since cosine is negative in more than one quadrant. All right, let's take a look at example 3 here. I'm first going to do tan inverse on both sides to undo tangent. Right? We want to get theta by itself. So we get theta equals tan inverse of negative 0.8921. Okay, let's go ahead and type that into our calculator. my calculator is still in degree mode because I want my angle for theta to be in degrees. Okay, so we type that in, end up getting negative 41.74 degrees. So theta equals negative 41.74 degrees. Okay, now there's one big reason why we cannot have a negative angle as our answer. Up here, it says that it's looking for theta to be greater than or equal to 0 and less than 360, and negative 41.74 does not fall within that. Okay, so I cannot leave that as part of my answer. Why in the first place would your calculator give you a negative angle measurement? Remember, we put tan inverse into our calculator. If you look up here, if you put tan inverse into your calculator, it's only going to give you angle measurements in quadrant 1 and 4. So when it gave us a negative angle, it would be somewhere down here, right? We need to find something that's coterminal with negative 41.74 that is actually a positive angle. So let's go ahead and do that really quick. So this would be our negative 41.74 degrees. Okay, and let's think to ourselves, what is a positive angle that would be coterminal with that? Well, if I take 360 degrees and I subtract off that 41.74 degree chunk, what would I be left with? I'd be left with 318.26. So this is going to be 318.26 degrees. So one of my answers for theta is going to be 318.26 degrees. Now, there's more than one quadrant where tangent's negative. All students take calculus. Yes, tangent is negative in the fourth quadrant, but where else is tangent negative? In the second quadrant here. So I'm going to draw in a line, and I'm going to use the same reference angle, 41.74. Okay, really our reference angle are positive angles, so I'll go ahead and update this one down here to being a positive angle. Okay, and let's go ahead and figure out where that terminal side gets us. What would be that original angle if it's 41.74 degrees short of 180? Well, I'm going to take 180 and I'm going to subtract off the 41.74 degree chunk, and that leaves us with what? 138.26. So that's going to be my other answer. Okay, if you're writing this in set notation form, it's best to go from the smallest number to the biggest number. Okay, and there we go. All right, in example 4, it's really tempting. You want to start with secant inverse on both sides, right? So that undoes secant, and we're left with theta equals secant inverse of negative 1.4389. However, we do not have a secant inverse button on our calculator. So a little trick that I like to do is rather than even starting the problem that way, I immediately like to change it into terms of cosine, right? We would normally use sine, cosine, or tangent, but because this is secant, I'd like to rewrite it in terms of cosine to begin with. So secant and cosine are reciprocals. So we can rewrite this as cosine theta equals 1 over negative 1.4389. And now I'm going to do cosine inverse on both sides. Use cosine inverse to undo the cosine that's next to theta. And on this side, we'll do cosine inverse as well. I'm going to actually write this in black. Okay, so we'll have theta equals cosine inverse of 1 divided by negative 1.4389. Okay, and let's go ahead and type that into our calculator. Again, it's still in degree mode. So we have cosine inverse, second cosine, of 1 divided by negative 1.4389. So I end up with 134.03. So theta equals 134.03 degrees. Okay, now that's not the only place where secant is going to be negative or where cosine is going to be negative. All students take calculus. Cosine is going to be negative here and here. So the 134.03 is my first answer, but I also know that I'm going to have a terminal side in the third quadrant as well. What is this reference angle right here? Well, to get the reference angle, I'm going to take 180 and subtract off that 134.03 chunk. And we get that the reference angle is 45.97 degrees. So I'm going to use that same reference angle right here, 45.97 degrees. Okay, so tell me what this angle would be. Well, it's going to be 45.97 degrees more than 180. So if I take 180 plus 45.97, what does that give me? That gives me 225.97 degrees. So that's going to be my other answer. I'm going to say 225.97. Really though, up here, for all of these problems, it was just asking to the nearest degree. So I'm going to make this answer 134 degrees, comma, 226 degrees. I'm going to go back and I'm going to make this example 3, 138 degrees and 318 degrees. I'm going to go back and make example 1, say 42 degrees and 138 degrees. And over here, we've already got 120 and 240, so that's already rounded to the nearest degree for us. Okay, I'll never take off for you being more accurate, but I will take off if you are not accurate enough. Okay, so in example 3, it says find the angle values and radians for theta to the nearest hundredth. So this one does say to the nearest hundredth. So it's nice that we got practice with that in the last example. Okay, we are going to be using radian mode now in our calculator. I know that because it tells us that it wants theta to be between 0 and 2 pi. Okay, so now that I've got it in radian mode, let's go ahead and get theta by itself. I'm going to use sine inverse on both sides. So we get theta equals sine inverse of 3 over 5. Okay, going over here, we need to make sure our mode is in radians, and it is. We're going to go to sine inverse of 3 over 5. Press enter, and we get 0.6435. Okay, we're just rounding to the nearest hundredths. So we're going to get 0.64. Now, we know that's not the only spot where sine is positive. Okay, looking at these 4 quadrants here, let's just talk about radians in general at each one of these quadrantal angles. Here is 0 radians. This is pi over 2. Well, another way you can write that would be 1.57 radians. Over here is pi, which another way we can approximate that would be 3.14. Down here is 3 pi over 2. Another way to approximate that would be to get 4.71. And then 2 pi, another way to write that would be 6.28. Okay, and we know that we got 0.64 originally. So 0.64 is going to be over here in the first quadrant. Now, based on all students take calculus, where else would sign be positive? Not only in the first quadrant, but also in the second quadrant. So I have to draw a terminal side there as well. And I'm going to use the same reference angle, 0.64. So I already got the 0.64 listed from the first quadrant, but what angle would end up in the second quadrant? It is 0.64 less than 3.14. So if I take 3.14 and I subtract off the 0.64, what am I left with? That's going to end up being 2.5. So I'm going to list 2.5 as an answer as well. Okay. The next example, again, we need to undo tangent. So I'm going to use tan inverse. Whatever I do to one side, we have to do to the other side as well. So I did tan inverse on the other side as well. So we get theta equals tan inverse of 0.9321. In my graphing calculator, I'm going to put that in. Second, tan inverse of 0.9321. We get 0.75 approximately. Theta equals 0.75 radians. Now, I know that that's not the only place where tangent's positive. Let's draw a picture. Again, this is 0, 1.57 radians, 3.14 radians. This is going to be 4.71 radians approximately, and then this is 6.28 over here. Okay, and we've got 0.75, so I know that's landing in this first quadrant here. All students take calculus. Where else would tangent be positive? Not only the first quadrant, but also the third quadrant. So I'm going to draw a terminal side there. And my reference angle from the terminal side to the x-axis is still going to be 0.75. Now, what would that original angle measurement be? We've already written the 0.75 in the first quadrant, but what angle would give us a 0.75 radian reference angle in the third quadrant? Well, in order to figure that out, I'm going to take 3.14 and I'm going to add on that 0.75 chunk. So we end up with 3.89 radians. So I'm going to add that to my answer. 3.89 radians is going to be part of my answer. All right, perfect. Over here, I'm going to start by undoing cosine. So I'm going to do cosine inverse to both sides. Okay, so we get theta equals cosine inverse of negative 0.4289. Alrighty. So theta is going to equal what? Well, cosine inverse of negative 0.4289 is going to give me 2.01 approximately. 2.01. And again, I know that there are more than one, there's more than one quadrant where cosine is negative. So let's think about that. We've got 0, 1.57, 3.14, 4.71, and 6.28. And we got 2.01. So that's going to be over here. Okay. All students take calculus. Where else would cosine be negative? Cosine's negative in the second quadrant, but where else? Cosine's also negative in the third quadrant, so I'm going to draw a terminal side here as well. Okay, in order to figure out what that angle is, we first have to figure out what this reference angle is. Okay, I know that this is 3.14, and then from here to here is 2.01. So in order to get that reference angle, all I'm going to do is I'm going to take 3.14 and I'm going to subtract off my 2.01 chunk. So we get 1.13 for this reference angle. I'm going to use the same reference angle down here in the third quadrant. Okay, so now tell me what this original angle is. What angle has a terminal side in the third quadrant with the reference angle of 1.13? Well, in order to get that, I'm going to take 3.14 and I'm going to add on that 1.13. 3.14 plus 1.13 is going to give us 4.27. And I'm going to add that to my list of answers. There we go. Okay. Now let's go over the Pythagorean identities. The most basic Pythagorean identity, or the most commonly used Pythagorean identity, is sine squared plus cosine squared of theta equals 1. Okay, sine squared theta plus cosine squared theta equals 1. That is the most commonly used Pythagorean identity. If you memorize this one, you can easily get the other two. If I start with sine squared theta plus cosine squared theta equals 1, and I divide every term by sine squared theta, I'm going to get my second Pythagorean identity. So what is sine squared divided by sine squared? That's going to be 1. What is cosine over sine equivalent to? Cosine over sine is equal to cotangent. So cosine squared over sine squared would be cotangent squared theta. And then 1 over sine squared would give you cosecant squared theta. All right? And then how do you think I get the third Pythagorean identity? I'm going to take sine squared theta plus cosine squared theta equals 1 and do what with it? Well, I'm going to divide every single term now by cosine squared theta. Okay. If I simplify this, what's sine over cosine? Sine over cosine is going to be tangent. Okay, so because they're both squared, we're going to have tangent squared theta. And then what is cosine squared over cosine squared? That's going to be 1. And then what is 1 over cosine squared? That's going to give you secant squared theta. Voila, there we go. Right, so in these examples in part 5, it says factor the expression and use the fundamental identities to simplify. Okay, so looking at example 1, I see that both terms have sine x in it. So I'm going to start by factoring out a sine x. Sine x times the quantity cosine squared x minus 1. Ooh, and instantly I know that I can use a Pythagorean identity. Anytime you see squared with the trig function or a 1, you should be looking to see if you can substitute in a trig identity. Which trig identity am I going to use here? I'm going to use this first one. You can see that if I were to subtract 1 on both sides, we would get sine squared theta plus cosine squared theta minus 1 equals 0. And then if I subtracted sine squared theta on both sides, how I would end up with cosine squared theta minus 1 equals negative sine squared theta. So all of this, cosine squared theta minus 1, what am I going to replace it with? I'm going to replace it with negative sine squared theta. Or in this case, our variable is x. So I'm going to say sine x times, we're going to do negative sine squared of x. So we end up getting negative sine to the third power of x. Okay. When we're simplifying, we want there to be less terms, less trig functions used, and we don't want to have fractions. Okay, let's take a look at example 2. Instantly, I'm thinking factoring. So I got to get it in the format where the highest or largest exponent is to the left and then the constants to the right. So I'm going to make this cotangent to the fourth u plus 2 cotangent squared u plus 1, just like that. Okay, we want to try to factor this. First times first has to be cotangent to the fourth. So I'm going to make this cotangent squared u and cotangent squared u. And then last times last has to give me plus 1. So the only thing that will multiply to give you 1 would be 1 and 1. Okay, I'm making it positive because all of the terms are positive in the original trinomial. Okay, now instantly I'm seeing the squared and I'm seeing the 1. And so I should be thinking, replace it with a Pythagorean identity. Okay, go back up here. Which Pythagorean identity does it look like we can use? It looks like we can use the second one. I just have to rewrite it. So I see cotangent squared plus 1. Oh, I already have it, right? Cotangent squared plus 1. Here's cotangent squared plus 1. What can I replace that with? I can replace it with cosecant squared. Make sure you're using the correct variable. So instead of theta, I'm using u in this case. And again, cotangent squared u plus 1. I can replace that with cosecant squared u as well. So my simplified form is going to be cosecant to the fourth of u. Okay. Over here, again, I'm thinking factoring. It looks like we're doing factoring by grouping. So in this first group, what do both terms have in common? Sine squared x. So we'll have sine x minus 1 still in parentheses. And here we want that second set of parentheses to match. So what would I have to factor out to get sine x minus 1? I'd have to factor out a negative 1. Perfect. Then looking at these two terms, again, let's do GCF factoring. What do those terms have in common? They have a sine x minus 1 in common, so I'm going to factor that out as the GCF. Okay, if I divide each term by sine x minus 1, what is going to be left over? Sine squared x minus 1 is left over, right? And instantly, as soon as I see that squared and the 1, I'm thinking to myself, can I replace it with a Pythagorean identity? Do we have a substitution for sine squared minus 1? Well, let's look. Let's just try to rework this. Again, I'm going to start by subtracting 1 on both sides. I'll go ahead and I'll do this in purple. So we'd have our sine squared theta plus, I'm going to actually write the minus 1 next. Sine squared theta minus 1 plus cosine squared theta equals 0. Then we have to subtract cosine squared on both sides. So we'll get sine squared theta minus 1 equals, looks like negative cosine squared theta. Okay, so this sine squared minus 1 is equivalent to negative cosine squared. So I'm just going to plug that in, replace it. Sine x minus 1, and then we replace that with negative cosine squared. Be consistent with your variables. So in this problem, I was using x. And I think that's really all we can do. There's no way to simplify sine x minus 1 any further, and there's no way that we can simplify that part any further either. So that's it. All right, now we get into double angle formulas. Actually, I love double angle formulas. They're super easy to use and really help simplify the amount of work you have to do. All right, so here's how you use a double angle formula. The first one is a sine u cosine u. All you do is you take half of whatever this leading coefficient is, and then you double whatever this angle is. That's why it's called double angle formula. So again, you take half of the leading coefficient, so that's why we see a over 2, and then we double the angle. So if the angle is u, that's why we see 2u there. Okay, so the second double angle formula is cosine squared minus sine squared. What we're going to do is just double the angle. So you're going to see that before when we had an angle u, now it becomes 2u. Okay, so Let's put this into action. This looks like our first double angle formula. So all I have to do is I take half of the leading coefficient, I write the word sine, and then I double the angle. So I do 30 times 2. So I'm going to end up getting 3 sine of 60 degrees. And that's it. Okay, this looks like the second double angle formula. So all I'm going to do is write the word cosine, or the abbreviation for cosine, and then double the angle. If it was 40 before, when I double it, now it's going to end up being 80 degrees. And that's it. Let's try some similar examples. This looks like the first double angle formula. So I take half of the leading coefficient, write the word sine, double the angle. If the angle was x before, now it's going to be 2x. So we get 5 sine of 2x. Okay. Again, this looks like the first double angle formula, a sine u cosine u. So all I do is I take half the leading coefficient, make that 4. I write sine, and then I double the angle. If it was 3x before, now it's going to be 6x. Bada bing, bada boom. Okay. This looks very close to the second double angle formula, except for you're going to notice the double angle formula up here has leading coefficients of 1, where this is 2. We're going to factor out the 2 first before using the double angle formula. So if I factor that out, we get 2 times the quantity, cosine squared of 3x minus sine squared of 3x. And now the part inside of the parentheses looks exactly like my second double angle formula. So I'm going to write 2, parenthesis, and I'm going to use the double angle formula. Write the word cosine, or the abbreviation for cosine, and then double the angle. So it's going to be 6x. So that's it. 2 cosine of 6x. Okay. Over here, that looks just like our first double angle formula. We have the leading coefficient, right, divided by 2. Write the word sine, and then double the angle. So if the angle was 2x before, now the angle is going to be 4x. Okay, now part E is really challenging. Before today, I wouldn't expect you to know how to do part E. Right? But you do have one of these that are really similar in your homework, so I want to go over this. Okay, this one's kind of challenging, so definitely watch this one. The first thing that I'm going to do is I'm going to factor out a 2. Both of these terms are divisible by 2, so let's factor it out. In the parentheses, we'll get 2 cosine squared of 4x minus 1. Notice the angle did not change when I factored out a 2. Now, as soon as I see the cosine squared minus 1, I'm thinking, oh, it's a Pythagorean identity. The only problem with that is that the Pythagorean identity doesn't have a leading coefficient of 2 anywhere. So we might have to be kind of creative. Instead, watch what I'm going to do. I'm going to replace 1 with something. 2 times the quantity, 2 cosine squared of 4x, minus, now what can I replace 1 with? What Pythagorean identity is equal to 1? Well, sine squared plus cosine squared is equal to 1. So I'm going to replace 1 with sine squared plus cosine squared. Okay, so I'm going to replace 1 with, in parentheses, sine squared x plus cosine squared x. And you need to make sure that you have parentheses. If you leave out the parentheses, then you're not going to think to distribute this negative sign through to both terms. That's extremely important. The other thing is you have to be consistent with the angles. So like here I had written x. I am not working with x. I'm working with 4x. So we want to make sure that we stay consistent. So you're going to see me write sine squared of 4x plus cosine squared of, let me give myself a little bit more room, 4x. That's extremely important. Okay? You want to be consistent with your angles. So let's go ahead and multiply that out. We're going to have 2 cosine squared of 4x minus sine squared of 4x minus cosine squared of 4x. Okay, I think we're looking good there. And now we're going to combine like terms. So because I have 2 of those cosine squareds here, and I'm subtracting off 1 of those cosine squareds, how many cosine squareds would I have left? I would just have 1 cosine squared left. So I'd have cosine squared of 4x. We still have our minus sine squared of 4x. Oh my gosh! And what is that? It's cosine squared minus sine squared. Am I going to use a Pythagorean identity or a double angle formula? This gets tricky. So I'm not going to use a Pythagorean identity because there's no way to manipulate this right here to give you cosine squared minus sine squared and have a substitution ready to go. Cosine squared minus sine squared, we are going to use the double angle formula. Remember, we rewrite it using cosine and then we double the angle. So down here, I'm going to use cosine and then I'm going to double this angle. So it's going to become 8x. So my simplified form looks like this, 2 cosine of 8x. You can put parentheses around 8x if you want. Since it's a monomial, those aren't necessary. You only need parentheses if you have a binomial, trinomial, etc. All right, last but not least, we get to take a break again. This looks exactly like the first double angle formula. We're going to divide the first leading coefficient here by 2, write the word sine, and then double the angle. Okay, and that's all, folks.